I'll start by giving you a perspective of what we're seeing here, because we're sitting in a beautiful room in Tel Aviv in high-rise buildings at 2023. But not a very long time ago, this entire area was sand dunes. This country has grown by leaps and bounds, and we are right in front of Independence Day, and the country is definitely going for changes, but it's important to get a perspective of how fast things are moving here. I come from Hebrew University. It's the beating heart of Israeli academia. The concept of a university was brought up in the first Zionist Congress in 1897, if I remember correctly. And then they thought about, wait a second, a university in Israel? Who for? It's not that long ago. It's 120 years ago. And the idea was ridiculous. There were hundreds of people, studying the Bible in Jerusalem. Everybody was still hiding inside the walls. This wasn't Oxford. This concept was taken only 20 years later by Albert Einstein and the president of the first Zionist Congress, Chaim Weizmann, who believed that this can happen. And they did what the only thing they could do, essentially go to the United States, not Europe, and raise money. They took a boat from London to New York. It was a very interesting ride. It took them a month. But during that month, Albert Einstein's theory of relativity was shown to be correct. So when they landed, there was an eclipse. When they landed in New York, he was an instant celebrity. Now, if this was happened slightly different, none of this would happen, but it did. So they raised about $40 million, and this was the first endowment of the Hebrew University of Jerusalem. Again, the concept. There was nothing outside Jerusalem in the 1920s. Very, very few neighborhoods at best. And still, just a few years later, Albert Einstein came, stood on the rocks outside Jerusalem, and gave the first lecture at the university, long before the State of Israel was founded. And it was the theory of relativity. That was the first lecture at the Hebrew University. I'm standing in front of you, I would say 90 years later, coming from the Hebrew University of Jerusalem, that recruited me from Harvard. And I am, at one of the top universities in the world. We are ranked either 60 or 70 worldwide, 7 Nobel laureates, and it's an innovation powerhouse. Yes, we get a lot of funding from the European Commission. I was very, very excited to get 2 ERCs and a couple of FP7 and Horizon 2020 grants. And we're also, building this ecosystem extremely fast. One of the things that we built is a biodesign program. A program where we bring together MBA students, engineers that come from my center, and medical physicians, and teach them how to look at the world in a different way, how to break from their academic views of what is important and what they should put their efforts into. And think about startups. Think about where is an unmet need, and is somebody going to be willing to pay to solve that? It's a program that has been incredibly successful for us. More than 250 individuals graduated over the last 10 years. We brought in Boston Scientific for the first time to Israel. We brought in Terumo from Japan. Regretfully, we didn't bring European companies to be interested in the biodesign program that we have. We had offshots in Technion, that just opened, Biodesign Israel, as well as Melbourne, Australia. We had 7 medical device startups launched just over the last 8 years in the field that is now we're calling bioconvergence, right? But it's there. And what's really, really exciting is that when you get those individuals that come from a university that has been growing exponentially, they think exponentially as well. Okay. They see the innovation around them and they want to take part of that. They create the first startup. So the first startup we created was Guided Medical. It was launched in 2013. It got FDA approval in 2018. It's being sold in, the products are being sold in Europe and the United States. But the same people that did it once go ahead and do it again, right? Because they learn how to be entrepreneurs. They learn from their mistakes, they made the contacts, and then they go and they do it again. So Itai Chayut actually built Scopia Labs. So he built Guided Medical, got successful, built it again. And now we have an ecosystem. An ecosystem that we would love to export to other places, but also changes the way that we think about how do we apply technology. I want to tell you a little bit about the companies that I created from European funding and that I think are going to change dramatically the things that are around us, but I wanted you to get this perspective of how fast things move in the Israeli ecosystem. Okay? We're talking about exponential growth, and this is critical to understand. So maybe we'll have a few words about it at the end. So let's start with tissue dynamics. Tissue dynamics was actually born when in 2010 I was invited to come to the Hebrew University, and I was writing grants in the for the European Union to try to get funding for the new lab. I met Catherine Verfeil, who was a professor at VUB in Belgium, and also people from L'Oreal and from Merck in Germany. And together we wrote a grant called HemiBio. It was a grant that was partly funded by the cosmetic industry, which had a huge problem. The biggest problem is that they couldn't use animals anymore to develop cosmetics in Europe. And by the European Commission, essentially trying to create new technologies. So we sat there, and I told both Catherine, and Gladys, and Phil that I think we can take human cells, make human organs, put sensors in them, and essentially understand how molecules work, how drugs work. So I wrote a grant about this. The grant was funded, we got a lot of money in, we had a lot of major breakthroughs, we started working with L'Oreal, but one of the things that was created was this cool partnership, not only with Catherine at VUB from the Stem Cell Institute, but also with the Fraunhofer Institute in Germany. They had the sensors that we wanted. And together, we created tissue dynamics. So now, we're about a decade later, but I want to show you where we got from that initial funding. So tissue dynamics is the world's first autonomous drug development platform. We're using human organs with sensors to actually understand how do drugs work or how diseases work. The company has strategic partnerships with ATCC, that's the American Tissue Culture Collection. It's a bank that has more than 4,000 models of human cells and tissues. As well as Beckman Coulter, one of the leading robotic companies in the world. We were featured in CNN, in Kathy Wood's FYI, as well as selected as one of the top organ-on-chip companies in the world last year. What is the problem we're trying to solve? The problem is that drug development is not working. The industry is essentially slowing down to a crawl. We're spending more than $240 billion every year, but getting less than 30 drugs approved. The cost of every drug is about $2.6 billion to bring one drug to the market. 88% of our clinical studies fail. And that's after we invest massive amount of money. Why is this happening? Well, the first thing that is happening is because we're still relying on small animal models. Rodents, rats, mice, that have different physiology, different genetics, and different metabolism than humans. Actually, 17% of the molecules that are toxic in rodents are not toxic in humans, and vice versa. So how many people heard about thalidomide? Thalidomide, horrible drug in the 70s, caused horrible birth defects. You didn't hear about it? Oh, yeah, you're not informed. So, big story. It's very safe in rodents. Horrible birth defects in humans. On the other hand, how many people heard about aspirin? It's a good rat poison. Causes developmental toxicity in rodents, very safe to us for the last 5,000 years. This is not the only problem. The second problem is that we have a huge crisis of replication in biology. About 75% of academic papers can't be replicated. So you publish a paper in Nature, in Cell, you put a lot of time and effort, and then other labs can't repeat it. In Amgen and Pfizer, it's about 75 to 89%. It's crazy. And it's not because people are cheating. Yes, that happens, but it's a tiny fraction. It's because of human error. Biology takes a lot of assays, takes a lot of experiments, takes a lot of technical work, and we sometimes make mistakes. The last thing is cell line misidentification, 30%. Think about it. You're taking cells that are supposed to be a liver or a heart, and you don't know exactly what they are, and then years later, it turns out that you spent a decade working on cells that you thought were liver, and were actually HeLa cells, cervical cancer. This happened multiple times. And all these errors lead to this problem. So what are we doing about it? So the first step is to solve the animal model crisis. And what we're doing is we're taking human cells and we're building organs out of them. So on the top, you can actually see this is a human liver. Published in Nature Biotechnology. It is metabolically zonated. You can keep it going for more than 10 weeks outside the body. This is the human heart. We just published in Nature Biomedical Engineering. It beats 66 beats per minute. It has an epicardium, endocardium, pacemakers, but it's only 0.5 millimeter in size. This is the human kidney. It was the cover of Science Translational Medicine. And this is a brain, a tiny brain, 0.5 millimeter in size, but it's a human brain. So it has human genetics and human metabolism. So you don't have to rely on rodents. But the next step is actually the most important one. So this is the human heart. You see that it's actually beating. But what you're seeing around it are sensors. Sensors that allow you to capture critical information about how does the heart work right now. And because I have those sensors, I can do experiments that are inconceivable in rats or mice or even in humans, right? Because I can't put sensors into your brain or your heart and take a measurement every second. Well, I can, but it's not going to be ethical. And then those sensors allow us to get data that essentially defines how does a drug work or how does a disease work. We can understand mechanism of arrhythmia. We can understand, for example, mechanism of fatty liver disease in a way that nobody is able to do. Now, what's really cool is that we can automate this because we have those sensors. So this is $2.5 million investment in robotics that was added on top of about $10 million investment in that sensor system. But it allows us to not only eliminate animals from the discovery, but honestly, eliminate humans as well. No human error. You see, this robot is making the organs. I don't need to take them out and put them on a microscope with an antibody. I have sensors. I can see which tissue formed and which didn't. I can take them forward. I can put all the drugs on them, see which drugs work. And I can use artificial intelligence to tell me, okay, these are the right hits. Let's take them to the next step. Let's find out what concentrations they work, What is the mechanism? Go back, change the drug while changing the mechanism, take it all the way to a clinical study. Essentially eliminating human error. I don't need a technician that wakes up every day at a different time, takes a different cell with a different antibody to a different microscope. Everything can be automated. And the vision here is actually going in the same way as the autonomous car, when you think about it. Yes, I'm taking it to a different world. But cars were invented more than 100 years ago, but the first time we put sensors in them was in the 1980s. Today, we have early warning systems. Essentially, we incorporate multiple sensors with a microchip that tells us, wait a second, you're going to hit this car, stop. But where we want to go, at some point, is toward an autonomous driving vehicle. Because we know how to drive. We just need to train a computer to do this. And once we have sensors, we can close the loop. Whether it's going to be next year, or 5 years from now, or 10 years from now, we're going to get there. It's very, very clear. Now, we are doing exactly the same in biology. That's why we're a bioconvergence company. So the first organ on a chip was in 2006, where the first company to integrate sensors in it, actually the only one that has the patents. We can now understand in 2021 mechanism of action. So connect the sensors with an algorithm to tell us what works and what doesn't, essentially an early warning system. So we are the only ones that can actually go toward an autonomous drug development platform, which is exactly what you see here. This is essentially how you should drive your vehicle, or how should you develop a drug, but in an algorithmic form for drug development, that a robot can actually make up its decisions how to go. And this works extremely fast. Right before the coronavirus pandemic, actually during the coronavirus pandemic, we found a mechanism that is unique to humans, didn't exist in rodents. For the moment we knew this mechanism and worked with Abbott, we could get clinical validation of our data in less than 7 months. And then finished placebo-controlled, blinded clinical study, a phase 3 clinical study in less than 24 months after that, with good results. And then another mechanism that we identified for the kidney, from the very discovery of the first kidney tissue to the actual validation of this data, clinical validation of this data in less than 12 months. I want to show you very, very briefly, I know that none of you are scientists here, but I want to show you very briefly how the data looks like. This is a kidney model that we validated, so it's a proximal kidney model, and one of the things that we did is look at a drug called Cisplatin. It's a very common drug in cancer. We give it for most types of cancer. The problem with this platinum-based drug is that we know it causes kidney damage, but we don't really understand why. You see, if you give it to rodents at very high concentration, you see kidney damage, but that's because of vasculopathy, increased pressure in the kidneys. There's absolutely no evidence that this is happening in humans. So we don't really know how it works. When we add this drug to our system, we see a fingerprint that looks like this. This is the sensors-based fingerprint. And the interesting thing is that if you wake me up in the middle of the night, like my kids, and tell me, what is this? I will tell you, this looks like a fatty liver disease. But it's not. This is actually kidney exposed to cancer medication. This is fatty liver disease. But the fingerprint is so close that a machine learning algorithm can essentially superimpose it. And guess what? It was right. We do see, when you give these cells cisplatin, you see essentially fatty liver disease in the kidneys. The kidneys start accumulating lipids in a way that nobody saw before. But now we have the mechanism, the algorithm can go back and also discover a solution. In this case, it was glucose absorption, and you add a second drug, and suddenly it goes away. And then you ask, okay, Is this real? So once you have this data, you can go back and dig into Hadassah's algorithm. So one of the cool things in Israel is that our HMOs are completely integrated. So we can get data from patients very, very fast. So you look at 247 patients in the hospital. Everybody that is taking the drug, and indeed, dark green, everybody taking the drug has kidney damage, expected. But those that take this drug together with another drug, with empagliflozin, the combination that we found, suddenly have less damage. Almost normal kidney function. And this was very surprising, because the second drug is actually to treat type 2 diabetes, which is supposed to cause more kidney damage, not less. So this is a combination therapy that can dramatically increase the safety of pharmaceuticals. And then the value proposition here is very, very obvious, right? We can do faster development with a fraction of the cost and a fraction of the resources. Let's take a deep breath, and we'll talk about a different company. Believer Meats is the second company that I founded. It's a company that I founded about 3.5 years ago, and it was a huge ride. And if I took you in the last discussion to the late 1800s now, I'm going to take you to the Ice Age. Most of human development didn't occur in this beautiful weather. We actually were, right next to the European ice sheet. And the weather is so bad, it was very difficult to eat. So when somebody managed to kill a mammoth, everybody was celebrating. And it's easy to understand why. If you are just gathering fruits and vegetables, like my wife, then you get very few calories and no fat or protein in your diet. When you manage to eat meat, like me, when she allows me, then you dramatically increase the amount of fat that goes into your body, but you also increase the amount of protein that goes in. And for a family of people living in a cave, more protein means essentially more babies. You increase the intake of the tribe, you can make more people. When you make enough people, you can go out of the cave and build a village and start agriculture. Then you can get protein and you can get fat. The protein is very, very clear. By the way, you have excess grain, you can also grow cattle, but the other cool thing is the amount of fat seems to be linked to the ability to build big brains. Because we need a lot of lipids in our system. And if you take a look at this is genetics cranial capacity, so how big is your head compared to time of non-human primates all the way to humans. And you can see the big change happened here 2 million years ago. And it correlates with the beginning of meat eating and actually the discovery of fire. Essentially making meat available for everybody. This increased dramatically our lipid content all the way to about here. What all this means is that we have 2 million years of evolution telling us to eat meat, which means that as appealing as this looks like to my wife, it doesn't generate an emotional response. This, on the other hand, does. We can smell this. We can smell this from 500 meters away. We know that our neighbor's neighbors is cooking meat, and we're craving it. The problem is that we can't make it anymore. We're done. We're using about 25% of the global water supply, 33% of our land to make meat, essentially every single acre and every single gallon we have. Now, we are at peak meat. You heard about peak oil? We are at peak meat. Now, whether there's an academic discussion of whether it came in 2019 or it's going to arrive in 2025, who cares? Right now, stock market reports of both Cargill and Tyson are saying the same thing. They can't meet the demand. That's why forests are burning in the Amazon. Okay, to get a little bit more soil to feed a few more cattle. This is without considering the 14% of global carbon emissions that are coming from this sector of the agricultural community. So for a while, we believed that the solution is right around the corner, that the solution is plant-based meats. You know, companies like Beyond, Impossible, making the right texture, and the IPO of Beyond Meat led us all to believe that this is indeed the future, but then 2021 happened and it crashed. It turns out it doesn't taste good. I have 5 kids at home. I'm a scientist, so naturally I run experiments on my children. So they don't know what they eat most of the time. And kids are really the best test scenario because they don't buy the hype. I buy the hype. You know, I like the technology, so I eat it in a burger bun with ketchup and it's fine. But if you give it to your kids, then one of the things that you'll see is that they'll tell you exactly what it tastes like. And they don't like it. So why don't they like it? Well, the texture is right, but the flavor is off. The flavor is off because we're missing this white thing. There are specific molecules in fat, animal fat, that when you grill them, release hundreds of complex polyaromatic hydrocarbons that you can smell from far away, and this is what you actually smell. This is what you crave. So we know our neighbor's neighbor is cooking chicken, right? We don't know whether baking cake. You know, baking cake or grilling potatoes would also generate polyaromatic hydrocarbons, just that we can't really recognize them. So the idea is that this is essentially what you needed, but right now, there's only one technology that can make animal fat, and that technology is cultured meat. So the concept has been around for more than 100 years, but it's relatively simple. You start from a muscle, you take cells from a muscle, you grow them in a bioreactor, and then you make meat. Relatively simple, right? The problem is that it's very, very expensive. So most companies are doing the following. They're taking stem cells from an animal, very unstable. You need a lot of growth factors to make them happy. They're growing them on microcarrier beads. Essentially, the cells have to stick to those plastic balls that you tend to detach them from those balls. So very low densities. The yields are very low. And then they're waiting for a month until they make a muscle. Now this works. It certainly works, but the numbers don't add up. You need about $100 per liter of media to grow them, and about $40 to grow a kilogram, so you get a beautiful, hamburger, but it costs $6,000 a kilogram. So Elon Musk is probably going to be able to afford it at some point. But none of us would. So what is the technology that we should be developing? So Believer Meats is a company that I founded and essentially try to develop a completely different scenario, different technology than everybody else. We raised the highest Series B in this sector. So in 2021, we raised $390 million. We were the first to break down the cost barrier, go below $10 per kilogram, and the first to build an operational plant. So what are we doing that is so different from everybody else? Well, we start by not growing stem cells. We grow fibroblasts. So stem cells are what grows your muscle. So you go to the gym for a month, and then your muscles grow by how much? 5%? At best. Very slow. On the other hand, every time I get cut in the kitchen, the cells that close the cut very, very fast are fibroblasts. And they close it in minutes. They grow very fast. And the other thing that they do is that they spontaneously immortalize. So we don't need any growth factors to grow them. It's very cheap to grow them. And they immortalize, that means they grow forever without any genetic modification. Actually, in the lab, we got to more than 1,000 population nowadays. That means that if you collected all the cells we grew in the last 3.5 years, you would have to the power of 200 kilograms of food. This is a big number. You want to know how big it is? It's more than the mass of the planet, which is nice. But it's also more than the mass of the Milky Way galaxy. Actually, even if the new James Webb telescope, the amount of food you can potentially make is more than the mass of the observable universe. Okay? That's the power of exponential growth. And then the other cool thing is that you can take them and you don't need those plastic beads. You can actually grow them as single cells, getting to very high cell densities, about 100, 130 million cells per gram, about 20 times higher than everybody else in the industry. That means that our factories can be a lot smaller, 20 times smaller. And now we can think about how to change this ecosystem. So I want to be conscious of the time because I think I take way too much time. And I want to give you some perspective of what this technology can do. So today, European farmers growing cattle need to wait 10 months from the moment that they got the cattle going all the way to the harvest. You need to predict what the cost of beef is going to be a year from now. If you have a virus infection, prion disease, you have to cull the entire herd. You lost a year of income. Okay? This technology would allow you to do this in 2 weeks. So you fill a bioreactor with cells and you harvest it in 2 to 4 weeks. Now, if something goes wrong, you flush it and you start again. What's more cool is that the same bioreactor system that you have in your farm can make any type of meat. You just switch and choose. You can make chicken, and then Christmas comes, so you move to pork, and then Memorial Day comes, so you move to beef. Okay? Choose. You don't have to be a single species farm. The same farm can grow all different types of meats. That means you can rapidly change and adapt to market demands. You don't have to wait 90 days for chickens or 10 months for beef. And the environmental impact of this are a fraction of what they are. So in beef, we're talking about 98% less land, 90% less CO2, 83% less water, but also in chicken, which is incredibly environmentally friendly. We're talking about 40 to 50% less CO2, land, and water. The big thing here is actually not CO2. The big thing here are land and water. We'll talk about this too, but in a second, but we're running out of water, even in Europe. In the United States, it's even worse. The Colorado River is completely drying up. And the second thing is that we're using too much land. You can release this land and you can make a big difference. And we've been really heading the way over here. You can actually see that we got to cost parity in chicken and lamb, and beef and pork are coming very, very fast behind it. I just want to show you two things. One, this is the facility, this is the factory we're building right now in North Carolina. $123 million investment. It's going to make about 10,000 tons. This is going to be the first cultured meat facility in the world, large scale. And I want to give you a perspective of what land use looks like before and after the cultured meat revolution. This is true for Europe as well, just that we have the numbers for the US. This is how much land is going to use to grow cattle. 654 million acres in the United States is used for pasture. If we need 98% less land, it means you can make all the same amount of beef in this area in cultural biotechnology. That means you can release all of this land and reforest. So Israel, and this is where I'll stop, Israel was one of the first and only countries to finish the 20th century with more forests than it started. But if we get this technology rolling, we can do the same for all over the world. We can finish the 21st century with more forests than we started. Just this can make all of us carbon neutral for the next decade. Just restoring those forests. So this is where I'll stop because I took way too much time, and thank you very much.